Good morning, guys. Happy Friday. It's Friday, April 3rd. Hopefully, you guys had a decent week and are kind of settling in. I know I'm sort of settling into my routine, getting used to this whole concept and everything like that. Fridays are going to be a little bit goofy, I'm discovering, because every Friday morning, us math teachers as a department are going to have a Zoom meeting online. So that's going to set me back a little bit with getting out your Friday morning videos. I try to have videos as much as I can posted by noon, but Friday morning videos might be a little bit later in the day just because we have an hour math department meeting every morning. So just kind of giving you a little forewarning or heads up there. At any rate, though, we're going to jump back in. We're going to move forward, plug along, trying to get through as much calculus as we can with the remainder of the year that we have. So, section 3.3 is called the concavity test. All right, so we're going to explain exactly what that means, and I think I can do a pretty good job explaining this in our little 15-minute window that we have here together. But before I get into the concavity test and what exactly that entails, I just want to build up to it by explaining where we're at in the chapter, okay? So to this point, here's what we've had. We've had a function, okay? Whatever, it does not matter what that function is, it's completely arbitrary. What we've been able to do with what's called the first derivative test is when we take our function, we find its derivative. That derivative then, we figure out its critical numbers. We figure out when the derivative is equal to 0 or when the derivative is undefined. Those critical numbers then, and I'm going to just hand pick a couple of them just to kind of re-explain something that I showed you guys earlier in the week. The critical numbers are the x values that make the derivative 0, okay? But if we're just thinking in terms of what the derivative is, we've said it a million times, the derivative is the slope function. So the slope is 0 when a curve tops out or bottoms out. So I'm just going to give you two of them here real quick. X equals -3 and +2. Those critical numbers are the points in what we've been trying to find is we've been finding the intervals where the function is increasing or decreasing, meaning going up or going down. And the critical numbers are the points where it stops going up and stops going down. What we're finding and what we've been doing is we've been finding our max and our mins, right? So if -3 is a critical number, maybe -3 represents the maximum. And everything to the left of -3, the graph is building towards that, okay? And then at -3, it tops out, which is, if we think in terms of our tangent line, it means that it's got a slope of 0. It's a horizontal tangent line, which is why -3 makes the derivative equal 0. And then maybe +2, let's just say it's +2, -3. +2, -3 is down here. So after this, the graph starts going down, right? But at a certain point, it bottoms out, which is, again, why the tangent line equals 0 at that point. So what we've been doing using the first derivative test, and there's a reason we call it the first derivative test. Some of you might be wondering, why don't we just call it the derivative test? Why do we call it the first derivative test? Well, it's because of what we're going to do today. The first derivative test allows us to find the maxes and the mins, the points where the graph stops going up or stops going down and changes direction in most cases. Okay? So our first derivative test allows us to find our intervals where the graph is going up. So from -∞ to -3, it's going up. From 2 to infinity, it's going up. And in between there, from -3 to 2, it's going down. Okay? What we're going to discuss today is called concavity, or more specifically, when a graph is concave up versus concave down. And I know you guys those are familiar, though you recognize them, you've heard them before. Concave up is when a curve, and this is kind of the real simple elementary way I describe it. Concave up is when a curve is a smiley face, right? And a concave down curve is any portion of a curve that makes a frowny face. And in between, in most cases, in between a smiley face and a frowny face is a single point where it changes. So like if you think about a general curve, like an S curve that does this, there are parts of this curve that if we just key in on them, they look like a frowny face. There are parts of this curve that if we key in on them, they look like a smiley face. And if you kind of just trace this, you can see that there's a certain point where the graph stops being concave down, like this, and starts being a concave up. That point is called, and you've heard it before, we've talked about it, a point of inflection. What we're going to do today is we're going to have a conversation about not when a graph is going up and when a graph is going down, but when a graph is concave up and concave down. And the points that we're going to find are the points where that concavity changes. They are the points of inflection. So if you haven't kind of figured it out yet and pieced this together, the first derivative test gives us critical numbers that represent maxes and mins, where a graph stops going up and stops going down. The concavity test is going to be the second derivative test, and it's going to look very similar. The work that you're going to do today is an exact replica of what we've been doing for the last week, okay? But by taking a second derivative and finding its critical numbers, those critical numbers will be the points of inflection of the graph. And everything on one side of the critical number will be a concave one way up, either up or down, and on the other side will be the opposite of that, concave up versus concave down. So all I'm going to do is I'm going to give you guys one example to go off of here, because like I said, I think you'll see that the work is an exact replica of what we've been doing the last week. Okay, so here's our function, f of x equals x minus 3 to the 4/3 test. Okay, we're going to keep it very isolated and very simple today. What we do to determine the concavity of a graph, not its when it's going up and when it's going down, but its concavity, is we do the second derivative test. So we differentiate, but we do it twice. So the first derivative here is relatively easy. It's just the chain rule. So it's 4/3 comes down, x minus 3 stays the same. Subtract 1 from the exponent, so 4/3 minus 1 is a third. Multiply that by the derivative of the inside, which is obviously just 1. So essentially that 1 goes away. It's just 4/3 x minus 3 to the 1/3 power. So if we were thinking about it, I'm just going to throw this off to the side here. If you're thinking ahead here, the critical number, the only critical value would be 3, right? 3 minus 3 is 0. 0 to the 1/3 power is 0. 0 times 4/3 is 0. Let's just kind of set that off to the side for a hot second, because you're not going to be focused on both of these today. You're only going to be focused on concavity today. So you have to find the second derivative. So I need to take this first derivative and differentiate it again. Bring the 1/3 down, multiply it by 4/3. That gives me 4/9. Leave the x minus 3 alone, but now subtract 1 again from the exponent. So 1/3 minus 1 is negative 2/3. Fortunately, the derivative of the inside is still just 1. So if we clean this up, here's what we get. We now have a fraction. So I'm going to write it as a fraction, a true fraction. There's 4/9. The x minus 3 needs to move to the bottom. X minus 3 raised to the 2/3 power, and the top stays the same. So it's 4/9, and then x minus 3 to the... Okay, so here's kind of the interesting part about this one. The critical number here is the same as the critical number in the first derivative test. So we're going to talk about what that means for us in just a second, okay? What we do, though, is the same thing that we've been doing. The first part of your questions are going to ask you to describe the intervals when the graph is concave up versus concave down. So what you do is you take your critical number and you break your graph, or you break your domain accordingly. So if there's only one critical number, that breaks negative infinity to positive infinity into two intervals. Everything to the left of 3 and everything to the right of 3. Capiche? Okay. So we do the same thing that we always do. We plug in a number in this interval and see what happens. Do we get a positive or do we get a negative? So we're going to plug in 0 and we're going to plug in 4. Anytime 0 is an option, we're going to try and plug it in and see what happens. Okay? So when we plug in 0 for this, we get 0 minus 3 is negative 3. We need to think about what 2/3 means as an exponent. That means it's negative 3 to the 2/3 power. It's a third root. Okay, the denominator of the fraction becomes the root. The numerator becomes the exponent. So all that really matters here, you guys, is this. This is negative 3 squared, which is positive 9. It doesn't matter that positive 9 is not a perfect cube. What matters is that it's positive. This is a positive number times a positive 9, so that's still going to be positive, and then it's underneath a positive 4. So if you think about it, by plugging in a 0, you get a positive second derivative. So when your second derivative value is positive, what does that mean? Which one of these is it? Is it concave up or is it concave down? And I mean, it makes perfect sense. Smiley face curve is a concave up. We're always happy when we get positive numbers. So a positive second derivative is when a graph is concave upward. So we'd say concave up. And then let's just test to make sure that in fact it is concave down on the other side. So when you plug in 4, right here, you get 4 minus 3 is positive 1. Wait a second. So positive 1 inside here. Oh, look at that. That's interesting. Positive 1 inside. This is kind of an interesting one. I didn't realize it did this, but you get another positive number here, all right? So what actually ends up happening is we get a positive second derivative. So that means that this is concave up as well. So what we basically say, and that's kind of unfortunate that this happened. I'm going to have to show you something different for it. This tells us that it's concave up to the left. It's concave up to the right. That means there is no point of inflection. This graph never switches direction. Whatever the graph of this 4/3 root ends up being, it's always concave up. So maybe there's something unique about 3. Maybe that's an asymptote or something like that. But this is kind of a unique one. Let me just give you because I don't want to take up a ton of time here for you guys. I'm going to come up with a separate example just to show incredibly fast here. All right, just bear with me here. I apologize. I thought that example was going to work and serve us both purposes because the second part of your directions are a little bit different. So if I give you this function right here, f of x equals x to the 4th plus x cubed minus 3x squared plus 1. I'm going to shorten this up substantially just to make sure that we don't talk too terribly long. All right, there's a first derivative of it and there is a second derivative of it. It would be really easy to find because it's just a polynomial. But basically what I'm going to tell you is this. You get critical numbers for your second derivative of -1, x equals -1, and positive 1/2, okay? I want to focus just on -1. What happens when you go negative infinity to -1 and then -1 to 1/2? When you do your second derivative test, what you end up with is you end up with a concave up portion right here and a concave down portion right there. So at -1, what does that tell us -1 represents? -1 represents a portion where, or a spot where the graph stops being a smiley face and starts being a frowny face. So that would be right there at -1. The second part of your directions don't actually ask you to talk about the intervals themselves. All they ask you for is to identify the points of inflection. So what you would do is when you realize that -1 is the x value where a point of inflection occurs, where the change in concavity occurs, all you have to do is plug that back all the way up into your original function to find the actual point of inflection. So when you plug -1 back up here, -1 to the 4th becomes +1, -1 to the 3rd is -1, so those cancel. So those are basically gone. -1 squared is +1, +1 times -3 is -3, plus 2 is -2. -1, -2 is a point of inflection. Okay? So, like I said, the work is very similar. You do the exact same tests. You find these intervals, you plug in a number in that interval, every other number in that interval results in the same, either a positive or negative second derivative. But what that represents is not a graph that's going up or going down, it's a graph that's concave up or concave down. If you look, everything in this portion right here of this graph is not doing the same thing. It's going down and then it's going up because there's a minimum in here. But at all points in that curve, it's concave up. It's a smiley face. Okay, so that's what the second derivative is getting at, and eventually we're going to put together the concepts of the first derivative and the second derivative, okay? So if you encounter any questions, do the usual thing, hit me with an email, and then I will either send out a clarification email like I did yesterday, where I just basically work out the questions and let you see kind of the results, or if we have a bunch of questions, I'll make a clarification video and send that out Monday morning. Okay guys, have a great weekend and we will talk to you later.